Hi, very good evening, all of you today who are attending this webinar session. So, I hope my screen is visible and I am audible. So, without further delay, we will start. So, earlier also we have discussed about the MRI fat suppression techniques. So, apart from that, today we are including some shimming techniques which may help to get a better fat suppression in your daily routine. Yeah, in this topic, mainly we are going to see what is the main fat suppression technique like, major fat suppression technique like stir, spare, spectral fat saturation, the Dixon technique, water excitation, and some shimming techniques. So in MRI, we are using hydrogen proton for imaging. All of mainly hydrogen composed of one proton, one electron, and there is no neutron. Like that, here actually in fat suppression here mainly we are aiming to differentiate between the fat spin and the water spin. The water always consists of two hydrogen atoms bonded to an oxygen atom. Fat is a molecules have series of carbon and hydrogen atoms like lipids. So before going to see, we need to know what is chemical shift. Chemical shift means there will be a difference between the resonance frequency between fat and hydrogen. That means water. And fat hydrogen has a lower resonance frequency if we are comparing to the water hydrogen, and we can able to differentiate. We can separate these two signal by mean of its chemical shift nature. So usually we are measuring this chemical shift by the unit of ppm, parts per million, and for water and lipid there will be a difference between 3.4 to 3.5 parts per million. So we can easily differentiate between two of them. First, we are going to see what is basically stirring is an inversion. Inversion.
You have entered as an attendee in listen-only mode.
Using this difference for separating our fat versus our water signal. So here you can see from 0 it is the longitudinal magnetization, this plane. We are applying this 180 degree excitation, 180 degree inversion pulse. Then this longitudinal magnetization tilting opposite direction. Then it is relaxed back to its initial position. That time it have a different relaxation pattern like fat and water have. So in this particular area, we are applying, after a particular delay, we are applying a 90 degree excitation pulse. This time, this fat spin have a zero magnetization, and the water have a higher magnetization comparing to the fat signals. So here you can see it is the fat magnetization is 0 and the water magnetization is higher inside, but is in negative inside. Anyway, it have some magnitude. That means it has some vector. So if we are applying a excitation pulse, what happened that the fat proton will not excited because it has zero magnetization in nature, and water have some magnetization. So only water proton will excited after some particular time. So from the first 190 degree time of inversion to the excitation pulse, the time delay we can call it as the time of inversion. That is called inversion time. According to that, fat or water, each and every tissue have a different relaxation, different TI, time of inversion time. That means if you want to suppress fat, you should use a 170 millisecond in 1.5 Tesla. If you are considering 3T, you should use around 220 millisecond to separate the fat and water. So this same technique we are using for flare also. That means for fluid suppression, but there we are using a long TA to suppress this fluid. Here you can see water have a higher relaxation pattern. That means it will take time to relax. So that if we want to suppress water, we need to apply a long inversion recovery pulse. So after that, we are using 180-degree refocusing pulse, and we are refocusing. Then we are collecting the echo. This is the basic technique which we are using in stir. So this stir is basically based on the difference in the T1 relaxation time of the fat and water. And the image is look like here, like this. It will give a better homogeneous fat saturation. And mainly we are using this technique in MSK, whole body diffusion, whole body screening, med screening, etc. There will be two types of stir sequences available. One is T1 stir and another one is T2 stir. Depending upon the area we are imaging, we can change the awakening time. That means T1 or T2. In T1 stir, mainly we are using a short TE if comparing to the T2 stir. But the TR is almost remains same, and the difference is the TE. Here we are using the short TE. So if we are using the short TE based stir, that means mainly we are using in MSK cases. It will give a better visualization of tendon, ligament, cartilage, and it will give a better differentiation between fat and this tendon, ligament, and the cartilage. And here we are using a weaker fat saturation method, because we don't want to suppress entire fat because we want to create some difference between fat and muscle. So we are using the weaker fat saturation mode in this MSK cases. And the other application is with the T2 stir. We are using in whole body screening and for spine examination, for med screening, etc. Here we are using a long TE to acquire this image. So if we are coming to the next method, it is called spare. So it is called spectrally adiabatic inversion recovery. So same technique with other vendors are providing spear. So spectrally saturated inversion recovery. The difference with spear and spare, I will tell you what is the difference. Here almost this method is also similar to our stir, but the only thing is that it is a selectively exciting. But in stir, what we have seen, it is exciting the fat and water at the same time. But if you are looking in spare, here we are only selectively exciting this fat protons, fat spins. How it is like? First, we are applying a 180-degree adiabatic inversion pulse. This adiabatic inversion pulse means it's a spectrally selected. That means it is a class of amplitude and frequency, and frequency modulated RF pulse. So it have a definite frequency and amplitude. It's only invert the fat spins, and this water spin remains constant. Here you can see this pink line denotes water spins and green line denotes fat spin. Here only this adiabatic inversion recovery pulse only selectively excite these fat spins, and the water spins remains the same. So what happened? This is a longitudinal magnetization. Whenever we are applying this our excitation pulse, what is happening that this after a particular time delay we are applying this 90-degree excitation pulse. In this time, what is happening that only our water protons will get excited. That means these fat protons already we have inverted by this selectively inversion recovery pulse, and it is remains zero at a particular time. That means after waiting for particular time, it will come to the 0 point. That means null point. That time our water spin have a longitudinal magnetization. If this time if we are applying 90-degree excitation pulse, what happens that only our water spin got excited, and it will contribute the signal, and the fat signal remains zero. So this is the technique which we have used in spare. And why it is different from sphere is different from spare. Here is the main difference between sphere and spare. So spare using a adiabatic inversion recovery pulse. Here you can see the first inversion recovery pulse from 0 to have inverted into minus, that is the opposite side. Then it is going to relax. Some point of time we are applying this our excitation pulse. That time fat spin is in 0. That means there will be no magnetization for fat, and the water has some magnetization. So after sometimes what is happened that this fat may regrow. That means again this fat signal may regrow. So what we need to do, we need to suppress this fat continuously. This fat magnetization we need to suppress continuously, so that we are using a adiabatic module in between each TR. So we can remain this fat spins signal steady state. So we will only excite this water protons. So but in sphere what happened that there will be only one excitation. That means only one inversion recovery pulse in that initial time which we are using. After that there will be this continuing this excitation and relaxation. But in spare we are continuously applying the adiabatic inversion recovery pulse to saturate our fat protons. That means we do not allow them to regrow. That is a major difference between spare and sphere. And because of this, spare will take a spare should have we should give some higher TR to occupy this adiabatic inversion recovery module. So these are the major applications where we can use this spare pulse. Like if we are using some large anatomy with a complex anatomy, like in neck or in pelvis area or like breast, so there will be very difficult to suppress the fat because of the homogeneity issue and this B0 homogeneity issue. So mainly we are using this steer sequence in bilateral breast examination in T2FS or T1FS, and also we are using this for wipe for dynamic breast acquisition, and in abdomen TSE spin echo as well as the 3D space, and in wipe also we can use with Dixon also. So wherever we can use, the better the fat suppression, because it is less sensitive to B0 in homogeneity. Also we can use in spine and MSK. The main advantage of this spare pulse is it is very insensitive to B1 in homogeneity, because that means the RF related inhomogeneity is very limited with the spare pulse, and the tissue contrast is not affected much, because only we are selectively inverting fat spins. Water spins remains the same. So there will be this pair module will not affect the contrast of that particular tissue, and improved fat suppression quality with less or without shading artifact due to this spare module. It is continuously applying this spare module in between the TR, and the regrowth of fat remains constant. And the main disadvantage of this technique is increase the minimum TR, because the pulse sequence diagram need to occupy this spare module in between each TR. So the minimum TR will be increased, and sensitivity to B0 inhomogeneity that is because this design constraints and the anatomy. And we can overcome this B0 inhomogeneity with a lot of technique, like we have better shimming available. We will discuss later in this same topic. So what is the typical problem with this pair? So here you can see this is the chemical shift difference between fat and water. Here you can see the water peak, and here you can see the here you can see the fat peak, and here you can see the water peak, and the difference between fat and water is 3.4 to 3.5 parts per million. Whenever we are applying this inversion, selective inversion recovery, that adiabatic pulse, anyway, sometimes this nature of fat, it is different. That means the composition of fat and water may be different, and the edges of this fat may be show sometime it is the some more it is occupying this water space also. That means whenever we are using this module, there will be a region, it is called critical region. So that time it will not, this spare pulse will not suppress that critical regions fats, so it may appear in our image as bright signal. So for that, for overcome that, we have some novel techniques I will show you later. So these are some example with spare pulse with normal fat sat. So first image spare pulse with white 3D white in breast acquisition. You know, you already know breast is a structure which can cause more inhomogeneous field because of the anatomy structure, and spare done a good job if you are comparing to normal fat sat, because of it is very less sensitive to B0 if comparing with the normal fat sat techniques. So spare we can use for any large anatomy with it will give a better homogeneous fat saturation. And this is another typical example, spare with haste, which we are normally using for abdominal examination. Here you can see first image haste with the spare and second with the fat sat. The edges you can see some of the area have some limit to suppress this fat because of the homogeneity issue. Because fat saturation technique need a better homogeneous magnetic field. If the area is off-centerly placed, our magnetic field may be distorted, and there will be a limit to suppress this fat. So next three technique basically based on the chemical shift based. The first one is spectral fat saturation. That means fat sat. We commonly called as fat sat. This is the technique which we are commonly using for our daily examination. That means the fat saturation technique. Here, how it is different from our IR pulse. That is, here you can see fat and water have a different chemical shift in nature. That means a 3.4 ppm. Here we are selectively exciting these fat protons, like which we have seen in our spare technique. This RF saturation pulse is applied only on the fat frequency peak, not affecting this water frequency peak. That means it is spectrally and frequency selectively applying RF pulse, and after that it will it will destroy all the fat magnetization, and after that we are using some spoiling gradient to prevent the regrowth of this fat magnetization in longitudinal plane, and transverse magnetization we can spoil by using this some gradient. And by using this selective frequency selectively this pulse RF pulse, the longitudinal magnetization will be get saturated, and only we can use this longitudinal magnetization of water spins. So what is the major advantage and disadvantage of this fat saturation technique? We know, because it is based on the chemical shift method, it is it may fail in low field system like 0.21, 0.3, because the chemical shift difference between fat and water in low field system is very less. So we cannot, it is very difficult to separate this fat and water peaks in low field systems. The advantage is the tissue contrast is not affected. The same technique which we have used in spare, this frequency selective, and it is only destroying the fat magnetization in the longitudinal plane, and the transverse plane it is remains zero. The main disadvantage is it is very sensitivity B0 and B1 inhomogeneity. Suppose if we are using a large FOV with the FS fat saturation technique, it may fail sometimes because of this homogeneity issue with the magnet, and with the complex anatomy like neck area, in pelvis, in those areas sometimes it may fail because of the anatomic structure. And in this, additionally preparation pulse is required to suppress this fat because of the selectively frequency selective technique. And if it should carry some additional frequency, additional preparatory pulse, then anyway this TR may get increased. So if you are applying this fat saturation technique, you can notice that your minimum TR is increasing to somehow around 100 or 200 millisecond extra, because we need to occupy this preparatory pulse also. So we need to check your TR if you are using T1 fat saturation technique in your 1.43 Tesla magnet, because there will be a limit, there will be a range for this T1 T1 contrast TR. If you are increasing your TR, you will lose your T1 effect. So you need to concentrate in your TR also, then you will get a better fat saturation technique as well as the T1 contrast. So next topic is related to water excitation. So this is actually water excitation is a good technique. It is based on the frequency selective technique, but the nature and the application of the preparatory pulse, it is different comparing to other technique. So here what is happening, that the minimum excitation for water, and you can see this is our pulse chain, this black color, and in green it is the fat, and in blue it is water. Here you can see the minimum excitation of fat and maximum excitation of water spins. So here commonly we are using some binomial pulse chain. So we can classify this by different ways, like how we are implementing this binomial pulse chain. So here you can see one by one. Sorry, 1:1, 1:1, 1:3:1, 1:3:3:1, 1:4:6:4:1. These are the binomial chains. How we are dividing this binomial chain of pulse, and how longer the binomial chain, that much better you will get the fat separation. That means that will only precisely select the water spins and only excite this water spin. So if you can increase this binomial chains, if you can increase the binomial chains duration and the direction, you may get a better fat separation. The commonly used binomial chain is 1:1. That means we can split it is into, if suppose it is a 90-degree pulse, we can split into 22, 45, 22.5. So we can split this or excitation pulse in a different chains, and we can apply. So how it is, we will see in this slide. Here you can see the fat and water protons. You can see the spins in longitudinal magnetization direction. First we are applying a 22.5 degree excitation pulse. So in that time, both the fat and water magnetization get excited by this first binomial chain pulse. That means the 22.5 degree pulse. Then anyway it is dephase. It is start to dephase. So we discussed fat and water have a different relaxation time. Based on that, fat will dephase earlier and water will take some time to relax because of this relaxation, T1 relaxation property of that particular fat and water. So here you can see it is excited to this point, and after that it is starting to dephasing. The first fat is dephased to opposite side, and water remains in the same side. That means both the water and the fat is in opposite side. In this situation, we are applying the second binomial pulse. That means a 45 degree. Then what is happened, that the fat and water get excited, and this water is excited from here to next 45 degree up to here, and the fat is excited from here to next 45 degree. That means it will come to this point. You can see there will be a difference. So again it is starting to dephasing. When we are turning off our excitation pulse, it will starting to dephase. So this time again fat is in opposite direction and water is in the same direction. Again we are applying the third pulse, that means the splitted to 22.5 degree excitation pulse. Then again what happened that it will come to its initial magnetization, that means the longitudinal magnetization, which the fat is in the first phase. You can see here the fat here it is in longitudinal magnetization will be the 0, the z in the same direction, that means the z direction, it will come to the same direction, you can see here. And the water spins get excited completely by our binomial chain of pulse, and up to 90 degree you can see here. And at the end result fat remains same, the initial point water get excited and it is turned to transverse magnetization. And now it has some magnetization in the transverse plane. So in this technique you can see here at the end fat remains same, there will be no magnetization in transverse plane, it is remains in longitudinal plane, and water is completely tilted to transverse plane and it has some magnetization. So if we are allowing this fat proton to relax, water proton to relax, we will get some signal. So this is the technique which we have using for water excitation. The name itself it is mentioning, it is exciting the selectively water spins. The main advantage and the application of water excitation is that it is a frequently used in low field system because it is very less sensitive to inhomogeneity and B1 inhomogeneity, as well as here we are not considering the chemical shift between fat and water, we are only considering the phases, in phase and opposite phase. That means a relaxation between fat and water. And commonly which we are in this technique we are using for knee, shoulder like extremities, as well as in orbit, sometimes for T1 post contrast also we can use this. Mainly we can combine this pulse module with any of the 3D and the 2D sequences. And the main mainly we are applying this special water excitation sequence for our desk 3D in knee, like all the 3D sequence I already discussed, which is compatible with the other sequence also. You can try it and you can see the difference between normal fat saturation and the water excitation. And the advantage is that it is reduced sensitivity RF related inhomogeneities, and no extra RF pulse is required because it is dividing its initial excitation pulse into 2-3 parts depending upon the binomial chain. How much we can divide this binomial chain, that much fat saturation will be accurate. And the another important thing is that it will not increase our TRT at a higher in a higher level if comparing to other fat suppression technique, because it is only splitting the initial excitation pulse. And because of that it is the SAR problem is very less. That means the specific absorbed dose rate is limited because of this excitation pattern. And also it is compatible for post contrast acquisition also. The main disadvantage, if we considering it is a disadvantage, it is a little bit sensitive to B0 in homogeneities. The last technique which we are using, the Dixon. So Dixon actually it is not a new technique, it is a old technique. It is invented from very past, but there will be some limitation to use that and limitation to use this technique because of the reconstructing algorithm, it is limited. And the time taken to acquire this Dixon sequence is huge. That means we cannot accumulate within our daily routine clinical studies because of the time constraints. So What happened in Dixon sequence is that the normal image with the fat and water hydrogen atom processing in phase, and the that is the first acquisition. The second acquisition take the fat hydrogen in out of phase. After that, we are using some mathematical calculation, that some mathematical iteration to separate this fat and water by adding and subtracting this in and opposite phase. We will see how it is happening. So this is an example of 3D vibe with the Dixon sequence. That means it is a gradient echo sequence. First, we are applying this radio frequency pulse. After that, we are using the slice selecting gradient to select the slice. Then phase encoding gradient. After that, readout gradient. Here, what is happening that here you can see this is the polarity. Here you can see some square box. This is the zero line. This is the line, and this will be the polarity. After phase encoded, first we are acquiring with a positive polarity or negative polarity depending upon the sequence design, and we are capturing opposite phase image. Then we are changing our polarity, that means the polarity of the gradient, and we are acquiring it in opposite phase. So in this situation we will get two phase, that means in phase and opposite phase in a single acquisition. After that, what is happening that we are adding and subtracting to get this fat and water image. This is the case of Dixon in 3D-Y, that means a gradient echo sequence. So what happens if we are using Dixon in a turbo spin echo? So here comes the time limitation in turbo spin echo, that means the fast spin echo sequence. In that first short system, our sequence pattern is the first short system will acquire this in phase. Then it is continuously acquiring this in phase. So it is in the first readout phase. This gradient is applying and only took this in phase information from this excited slice. And the second short and the second acquisition pattern, we are acquiring this opposite phase. Opposite phase by changing the T little bit, because fat and water have a different resonating frequency, and we can acquire with a with a T difference. That means there will be a T change, echo time change between fat and water precision. So by application of different shorts, we can acquire this in phase as well as the opposite phase. So if we have in phase and opposite phase, we can calculate by using some mathematical reconstruction technique. I will show you later. And the time comes a huge insight. That means the first shot it acquiring the entire in phase image, and the second acquisition it is acquiring this opposite phase data. So both the acquisition will take separate timings. So it is increasing the time. That's what Dixon have some limitation in if you are considering the time. But the fat saturation is considerably very good if you are comparing other fat suppression technique. So for avoiding those time constraints, we are implemented a new technique. It is called fast Dixon. Here it is also a spin echo based, that means a fast spin echo based technique. So first we are acquired with a in phase and opposite phase separately, but in fast spin echo what happened that we are changing the polarity of the gradient as in positive and negative, and simultaneously we are acquired in phase as well as the opposite phase in a single excitation. So we can avoid these time limitations by using this fast Dixon techniques. So nowadays in most of the Siemens MRIs are using this fast Dixon as a routine. It will give it. We can acquire the half of the normal Dixon time and give a better fat saturation also. So how we can create this fat and water image? This is a complex step. If you are considering any of the fat saturation like spare, normal frequency selective or water excitation, this will be the Dixon will be the most complex reconstruction algorithm which we are using. So anyway, first we are acquiring this in phase and opposite phase. So here you can see this is the in phase and this is opposite phase. So each and every MR image, there will be two things: the phase image and the magnitude image. Usually, we are only using the magnitude image for the daily routine. That means the clinical purpose, and we are not considering the phase data anyway. In some applications like SW or phase flow study, in those cases we are using this phase contrast. But in all other examination, we are not considering the phase data. But for this Dixon reconstruction, that means the fat and water separations, we are using this phase data for our field map. How it is working, we will see in this slide. So anyway, this is in phase and it have a magnitude and phase. This is opposed phase, it have a magnitude and phase data. So by filtering from this in phase and opposed phase, anyway, it have some field inhomogeneity because of the patient anatomic structure and the RF and this our B0 inhomogeneity. Anyway, there will be a phase shift. Sometimes field we can call it as a phase difference and a field inhomogeneity. And for avoiding that field inhomogeneity from our reconstructed image, we can use some field map for avoiding this in homogeneity artifact. So that anyway, we have a in phase map, in phase data and opposed phase data. We are actually minusing from in phase to opposed phase. That means in phase minus opposed phase. Then we will get a phase map. This phase map we are using as the field map, that which is using to correct the fields. So this field map help to avoid some in field homogeneity artifact which we are causing when we are acquiring this Dixon sequence. And this is the one just a simple technique which we are using for this homogeneity correction. After that, we will get in phase and opposed phase image. From this, we can calculate our fat saturated image. How it is for water only image. That means a fat saturated image. The in phase we can add in phase and opposed phase. That means we can add image and we will get the water only image. If you are using in phase minus opposed phase, we will get the fat image. So we can easily filter out this data, but it is a complex process. There will be so many things are related to this process, like uh, phase swap, global phase swap, or the field inhomogeneity depends artifact. So many things. That's what it is. Have some complex mathematical reconstruction technique which we have using to separate this fat and water. Anyway, with a single acquisition, we will get 4 set of image. That means in phase, opposed phase, fat image, and the fat saturation. That means the water only image. So mainly this in phase and opposed phase you can use for in some abdominal imaging like liver hemangioma in liver mets, or in those cases this in phase and opposed phase image will help in clinical scenario. And if you are acquiring this Dixon technique, you can acquire this in phase and the fatty only image. That means if you are using a T2 Dixon, you will get a T2 image as well as the T2 FS image, because in phase image is there and the separated fat water only image is there. So you will get a 2 set of image in a single acquisition. In that way also Dixon will help you to acquire in a better way. So next we are going to see the shimming technique. What are the major shimming techniques and how it will help in your daily routine. So if you are considering the homogeneity, what is homogeneity? Homogeneity means the how is the magnet homogeneous. That means the magnetic how the magnetic field homogeneity, how much the homogeneous the center of the magnetic field. And for making our magnetic field maximum homogeneous, we are using a process. It is called shimming. Shimming in the sense nothing but it is a process to optimize the magnetic field as much as possible as homogeneous. So there will be so many techniques which we are using to make the magnetic field homogeneous. Usually we are measuring the homogeneity in parts per million by diameter per spherical volume. So at a given FOV, how much the parts per million, we can calculate by some mathematical iterations. By that, we can calculate the homogeneity of a particular field. For a routine examination, 10 ppm is sufficient for routine examination. If you are considering the spectroscopy, it is required a highly homogeneous magnetic field. In that time, we are using 0.01 ppm homogeneous magnetic field for acquiring this spectroscopy. That's what, before starting the spectroscopy, it will take so nearly 40 to 1 minute to make the magnetic field homogeneous. So many background processor you can see running, pre-scan, adjusting, water suppression, so many background processor you can going to happen. You can see while we are doing your spectroscopy examination. And we can classify this shimming into two: active shimming and passive shimming in the time of fixed, and and another shimming technique is called dynamic shimming. So fixed shimming means there will be two types: passive and active shimming. Passive shimming in the sense, when we are installing the magnet, we are using some kind of iron pieces. That means some iron or steel pieces which we are using to make compensate the magnetic field homogeneity. That means we are using some computer programs to calculate the homogeneity, and we can calculate how much iron or this metal is required to compensate that magnetic field. Like that way, we can homogeneous make the magnet more homogeneous. And the second one is active shimming. The active shimming means it is using some kind of specially designed coils which we are placed inside the cryostat. When we are installing, we are calculating this magnetic field homogeneity, and for making this magnet much homogeneous, we are applying some certain amount of current inside that coil, that shim coils. So this current will last all the time in that special designed shim coil, and it is required only one time. That means whenever we are installing the system, that time only we are applying this active shim coil current. So it will remain same and the constant. That's called, it is fixed. It is in the category of fixed shimming. So the second one is dynamic shimming. Dynamic shimming in the sense which we are using when we are doing some sequence, like if you are doing a T2 brain. So that time you can see inherently some process is going on. You can see in the downside of the monitor some pre-scan adjustment, tuning, receiving coil tuning, like that. That is called dynamic shimming, the patient-wise shimming. So anyway, whenever we are putting the patient inside the magnetic field, the field get inhomogeneous. So for making that field homogeneous, we are using this dynamic shimming. That means it is a patient-specific shim technique. Next, we are going to see what is semi-automated adjustment. So most of you have mostly tried this technique in spectroscopy examination. Whenever we are, not only spectroscopy, all the cases you can try this semi-automatic adjustment if you are considering some fat saturation issue. In those cases, you can find this tab from this options adjustments in your system, in your Siemens system. From that, you can adjust the inter shim value, P1 shim, and the frequency correction, and as well as the 3D shim also. You can change the gradient current as well. So mainly this semi-automated adjustments we are using in spectroscopy to get a less full width half maximum value to get a better spectroscopy. Considering some normal fat sat, that means our chemical shift based method, fat sat method, we have some novel technique for this fat separation. So this is the contrast card. Inside the contrast card, you can see the fat saturation tab. Here you can see 3 dots. Inside that, there will be a region fat saturation is available joints. So if you have problem with your joint, sometimes in your angular foot or finger, limitation to suppress the fat because of the inhomogeneity and this our anatomic structure. In that way, here you can see you can use the specially designed joint fat suppression. That is a region-based fat suppression technique. It will give a better fat suppression for your anatomy. So how it is, normally we are using a Gaussian shaped frequency selective pulse. So sometimes the edges of the fat may miss because of the off center frequency. For avoiding that, we are using a sharper pulse, which is very closer to the water spin. So we can precisely suppress this fat protons. Here, this joint, specially designed joint fat suppression techniques works. That means it is recommended for small joint, and when using this joint frequency selective pulse sequence, it is very less sensitive to B0 inhomogeneity because of this Gaussian pulse shape design. And the another thing is that if you are using this spare also, there will be 2-3 options are available for suppressing different anatomy regions. Like here you can see near to that spare pulse sequence card, there will be 3 options available. Default for all the anatomy, like you can use in any anatomy, and the second one is abdomen and pelvis, the third one is thorax. For selecting this spare pulse, there will be a difference. Here you can see this is the default spare pulse which we are using for normal application, and this is the spare pulse which we are using in the thorax mode. Okay, the main difference is here that the frequency difference. Here you can see, here we are using a wide band pulse to suppress the entire fat. Okay, and the water will be same, and the difference is minus 255 hertz. With comparing this our spare module and our fat spin, and this frequency difference is notable with the spare pulse in thorax and abdomen. How it is like, here you can see the difference is reduced. In abdomen and pelvis spare module, the size it is increased. We are covering some more part in this water signal, so we will get a better fat suppression in the time of, if you are comparing our default fat suppression. Here the frequency difference is reduced if you are comparing to a normal thoracic spare pulse. So another some important options that some B0 mode, that means the B0 magnetic homogeneity mode is also available in newly system. Like you can find that options in your program card system. Inside adjustment, you can see the B0 shim mode. So initial days, the previous system or older generation system, we have using tune up and the standard mode for all the examination. So most of the examination in our old Avando, in old Avando system, we have using the standard system for all the B0 shim mode. And tune up which we are using in some places, which is required a more precise tune up, more precise in magnetic field homogeneity. And the new system, we have some selective tune up method for neck area, cardiac, foot angle, and abdomen. So by selecting this shim mode, it is automatically adjusting your shim volume according to that anatomy and design of that particular B0 shim mode. We can try this. We can notice how this cause the difference in your fat saturation. And the next option, it may help you sometimes if you are regularly doing some MSK image examination, like knee, shoulder, etc. Here, all the times you may face that the off-center imaging. Sometimes in shoulder, you may face that near to that bore, there will be some limit to suppress that fat. That means due to this inhomogeneity. So basically, it is not. It is inhomogeneity. Basically, it is caused by inhomogeneity. But the main issue is to linear eddy current, which we are facing in that edges of the magnetic this bore. That means our FOB. So how we can avoid? For that, in that sequence card part 1, you can see this flow compensation. So usually in axial slices, we are using slice as the flow compensation. In coronal or sagittal plane, we are using read as the flow compensation. Usually which we are using the same. But in the case of extremities, if you are facing some problem with your fat separation, that means in the edges of your anatomy, you can use the flow compensation as read instead of slice, because this read pulse will reduce the eddy current. Why and how? That means anyway we are using flow compensation. Flow compensation means this is not a pulse diagram. It is actually we are using a gradient also. Actually, this gradient plays the flow compensation role in that place. So if we are applying a linear gradient over there in that read direction, it will reduce the eddy current in that area. So here you can see the difference. Here we are no flow compensation we have used, and the edges which is near to our magnetic field, the homogeneity is reduced because of the eddy current. Whenever we are using the flow compensation in read direction, it will help you to compensate the eddy current by applying this read flow compensation in gradient in read direction. It's the same technique you can use in wrist if you are facing some issue, wrist, shoulder, knee, all the MSK cases. Yeah, third one is how to help your shim volume with if you are considering fat and flow artifact. Suppose if you are doing a cardiac case, or suppose if you are doing a small anatomy and you are using the standard shim, it is a bigger volume, or tone up shim, it have a bigger volume. So if you are reducing the shim volume, you can see this green line, this is the shim volume. You can find in your graphical segment, there will be the last option is shim box. If you are to turn on this shim box, you can see this area, this green area, this is called the shim volume. And here you can see my occurring volume, that is in yellow in color, and it is very small if you are considering the entire shim. So you can reduce the shim, because I don't want the unnecessary area outside this my FOB. You can reduce the shim and you can make the magnetic field more homogeneous, your acquisition FOB more homogeneous with respect to your external magnetic field. And in sometimes it will help to better homogeneous fat separation. If you are using this in your cardiac examination, like if you are using some cine examination, you may face some flow artifact, right, in 3T especially. So in that time you can reduce your shim volume and you can make your magnetic field more homogeneous, and reduce the shim volume, you can improve your image quality better, because the same technique, same shim volume reduction technique which we are using in our cardiac tortogen as well, it will give a better result. So you can try with a manually adjustment also. So this will help you better acquisition of your cardiac examination as well. So the next thing is frequency confirmation. So basically this frequency confirmation usually we have seen in breast examination, because it is a large volume, and it have a very large amount of fat tissue inside. So for getting a best and good fat saturation in breast examination, always do the frequency adjustment, confirmation adjustment. That means you can find it in your adjustment tab. You can find its confirm frequency tab nearly here. There you can assume your dominant fat and assume your dominant silicon if the patient has some silicon implant. So if you are running this confirm frequency box, after doing this shimming adjustment, all the things, system will give a graph like this. Here you can see fat and water. So always fat peak will be in the left side and water peak will be in the right side. From here, consider this is the water peak. This will be 0. From 0 to 220 Hz, we can find the fat peak. So that way you can easily select the center frequency of fat and water. And by this selecting the center frequency of water, you will get a better fat homogeneous. That means a better fat saturation in breast examination. Sometimes you can find this in some diffusion, sometimes in whole body or abdomen diffusion you can find. For just selecting the center frequency of water, it will help you to get a better homogeneous fat saturation for your daily routine. So same way you can, if you turn on this silicon also, The third peg you will get left side to water. So sorry, fat. This will be fat. Water will be 0. Fat will be 220 heads depending upon the field strength, and silicon will be nearly 320 depending upon the field strength. If it is a 3T, it is double, nearly 646 double, nearly 640. Depending upon that, you can select your frequency offset. So thank you for your attention. So this is from my side. If you have any doubt